Hi, everyone. This is Soumya, I'm Aditi and Ying, and we are going to talk about all the Presto native features that we have built at IBM over the last 6 months. So Soumya is going to talk about custom functions, custom user functions, and dynamic loading for Presto C++. I'm going to talk about some new cross-optimizer and runtime optimizations for streaming top-end and CTE, and Ying is going to talk about shuffle improvements all across the board. So we'll just do our presentations one after another and leave time for questions at the end. So Soumya will go first. Yeah.
All right, thank you. Thank you for the introduction. All right. Okay. Try the other clicker. Oh, yep, got it. All right. Okay, so hi, everyone. I'll be talking today about the work that's going on in Velox right now regarding dynamic loading. And I will keep this short because I don't want to keep anyone from figuring out what Ying and Aditi are up to, so I don't want to be that person. But let's paint the picture. So what is going on right now? So in Velox, the only way to add any like custom functions, types, connectors right now would be to do it built-in. And for anyone who's worked in the Velox code base, you might be familiar with what that effort looks like, but let me give you a quick overview. That can be cumbersome in that it requires a lot of understanding of the code base to begin with, to know where to put the code, where to write the code, what to do with the code, and all of that, right? At the same time, it can also be time-consuming from a compilation standpoint, because compiling and recompiling can take longer time and make your executable larger, as all of your functions, connectors, types, and everything are sitting in the code base, right? So the solution is we have now added the ability for users to dynamically load any functions, custom functions that they would like. In the future, we also want to extend that to types and connectors that is currently in the work. So what does that look like? How would that look like? Let's explore this use case. So let's see how Presto C++ is going to load dynamically loaded user-defined functions, UDFs, and use this config-driven wrapper into like using the Velox's dynamic library. Okay, so I know this looks like a lot of code, but let me walk us all through this. So I labeled everything 1, 2, 3. So the big one is the CPP file, the C++ file. Next to it, we see the CMake list, and underneath, there's a JSON file. So these three elements are going to be needed for you to get started with these UDFs. For the CPP file, there we go. So much better. Most of this code that you're going to be looking at is boilerplate. What I want us all to take notice at is, you know that line that says result equals 1, 2, 3? That's where your implementation for whatever you want to do with your user-defined function will go. Similarly, I see inputs and outputs, which you can write according to whatever types you want, whatever you would like that to look like. At the very bottom, the bottom arrow over there, there's a register Presto function. In there, you can find the name of the function. So the important thing to note here is that everything else is boilerplate code, and we want your implementation to be the only thing that you're worrying about right now. So how do I take the C++ file and turn it into the shared library that I promised you all you can load dynamically into your Presto workers and coordinators? So on the right side, there's a cmakelist.txt. Now, this is one of the ways that you can get started and get up and running. But this is, again, essentially some copy-paste boilerplate that the only thing that you will be that we would request you to change, and of course you have free will, but is going to be the name of that library so that you can find it afterwards. Lastly, that JSON file in the bottom is going to be the config-driven wrapper layer. Now, what does that mean is we want to have some sort of validations for whatever function that you're going to be loading. So I'm going to show you from these arrows what we are looking to validate. One, the file name over here is going to have to match up to what we just defined in the CMake list, or the name of the shared library. And then there is a few other things. For instance, the name of the function, dynamic Velox con, how convenient, and our parameters, return types, and whatever else that you would like to be able to check, you can take a look here. And I know this looks like a lot, so there is extensive documentations and examples that we've left for you to explore this on your own time. And I've linked the documentations to these slides as well. So once you've set this up, how do I get up and running? All right, so for that, we would ask everyone to take their workers and check their config.properties file. In that config file, you would add your plugin.dir property, your plugin.config property to the paths of these files that we just created, the shared library and the config JSON file. In addition to that, when you start your coordinator and your worker, the Presto server is going to do all the validation and load these user-defined functions dynamically. All right, so that's all for me.
So our next set of features are around performance. And we sort of came up with these features examining our TPC-DS query workloads, but these are really broadly applicable features and are useful across the board. So the first feature is something we're calling streaming top N. And if you see like the TPC-DS profile here, right, there's one query that stands out, and that's Q67. And if you see the runtime, I mean, the release 288, which is some time back, the native engine had a runtime of 31 minutes for 100 queries, and 9 minutes out of those 30 minutes were in Q67. So it's a pretty bad query. So we kind of wanted to, we spent some time trying to understand Q67 and what we could do there. And so on the left-hand side, I've projected like Q67. And if you see what that does, is that there is an inner like subquery that does like this massive join, and it has a group by rollup to compute like aggregates for different sets of columns. But what happens at the outer layer is that we do this rank function. So, and that rank function basically kind of separates the rows, it partitions by category, orders by the sales that it has computed as an aggregate, and is only looking for actually the top 100 rank rows in every partition. So like your inner massive join has like 386 million rows, but the result is only like 1,100, well, 1,000, around 1,000 rows. The rank computation today is done with this window function, window operator. And the window operator today, what it does is it gets all the input, stores it in an internal row container, then it does a big sort at the end of seeing all the input, where it uses the partition by and the order by to sort the data, and uses that to demarcate the partitions. And after you like identify all the partitions, it computes the rank across for all the rows, and then like post this window operator, do we do a filter to just take like the top 100 ranks. Now this is very inefficient, and we can do much better. So at the very least, we want to push the filter into the rank so that the window operator doesn't really generate that many rows, but we can do better than that. And so rank can be computed in a streaming fashion. And so you don't really need to see all the data and then do this massive sort. Rank can be computed on the go. And the partition can only like retain the 100 rows per partition, and so you won't have this massive memory sink and like intermediate data that you need to keep. for this query. And so with these two optimizations, we saw that the latency for Q67 fell like from around 400 seconds to like 146 seconds. So how we did this is that we wrote this new top-n row number, top-n rank operator. And what this does is it does like a streaming top-n rank computation. So basically, it uses a hash table to identify the partitions using the partition key. And then for each partition group, we maintain an accumulator with a priority queue for just the top 100 ranked rows. And as every row comes in, we decide whether it should remain in the queue or leave the queue, depending on its order by key and its rank in the partition. And we've implemented this logic for rank and dense rank functions. And since this is a new operator, it needs planner changes. And so we added a planner rule to identify the query pattern where you have a rank filter. And we will now use this new operator instead of the window. The second optimizations are for CTE with clause. So SQL users use with clause to identify like common tables that are used multiple times in a query. SQL semantics dictate that with clauses should be like computed once across the scope of the query and reused each time the with clause is used in the outer query. But this is not what happens in Presto today. Presto expands the with clause just like a view, and it is recomputed each time. Now, this can get ugly, and because CTEs can use other CTEs, and so what that means is that you're kind of multiplying the number of times you might expand like the innermost query. So like this is example Q64, where there is like CSUI, which is like the innermost layer of the with clause that is used in the next layer of the with clause, which is computing like cross sales. And then cross sales is used in like the outer query, which is actually doing a join, a self join of cross sales. And so like the innermost query is going to be like repeated multiple times. So this is very prohibitive. And we wanted to make like with computation closer to the standard by actually doing common table like materialization. And so again, this has a whole lot of optimizer work because figuring out like which common tables you actually want to materialize and reusing them in the query, it's a complicated problem. And there are many rules, like you want to ensure that your with query is used more than once. If there are common filters, you want to push them down in the with clause so that it's more efficient. But so I've linked this article that Jay from Uber wrote about the planner work that's needed for executing CTEs. But in just a quick summary, right, what we do for CTEs is that we look at the CTE references, and they are actually, instead of expanding them, they are separated into a producer and consumer part. And so the producer is like a writer. You do like the inner subquery, write it to like a table. That table is only for the lifetime of the query. And then the written table is reused in all the references in the rest of the query. And in order to ensure that we have the write sequencing, that the write pipeline completes before the read pipeline, there is a sequence operator that the scheduler works with. So we made all the runtime changes to support these new CTE reader writer configurations, and saw a lot of improvement using CTE in the native engine. And we're doing a lot more experiments because right now we're using just the regular like ORC and Parquet reader, but we want to use more efficient like serialization, deserialization formats. And if possible, we want to do like a proper streaming CTE so that we don't have like writers and readers. So that's that. So I'm going to hand it over to Ying.
That's quick. So the next, I'm going to briefly talk about Presto C++ shuffle performance. This is an ongoing work. It's far from finished. But yeah, it's quite interesting. So I will first talk about so what consists of the shuffle cost and what we have done so far, and we'll briefly go through the design, implementation, and so on. But these are in a very preliminary stage, so just some data points and discussions. All right, so why do we look at shuffle? So this is because when we are running these benchmarks like TPC-H and DS, we saw that the shuffle cost is quite high. So for example, in TPC-H, partition output and exchange and local exchange, they comprised of over 40% of the total CPU, and this is very high. So in this benchmark, you're supposed to see some big aggregations, but this shuffle thing is too high. And also TPC-DS shows some similar numbers. So let's zoom into one particular query, TPC-H query 9. So this query has the highest shuffle cost in TPC-H, the 22 queries. So as you can see, this partition output itself takes 30% of the total CPU, and the next one, exchange, takes 29, and then the next one, table scan, 20. So yeah. So then we ran some CPU profiles. We saw that a very high percentage spent in Exchange I/O and HTTP I/O. So these network threads are taking a lot of CPUs. So this is what our research team is working on a binary exchange protocol, which tremendously improved these two parts. And also, I did some tests just last week. So because this query shuffles a lot of data, so we thought maybe compression would help. So to run this, we have to introduce a new session parameter, exchange compression codec. So this is new, so you guys are welcome to try. So currently supports every compression codecs, LZ4, gzip, DSTD, and so on. So with LZ4, unfortunately, this doesn't help, and it's even slower, 2x slower. So so we'll have to do something else. So my talk is mostly, in the driver part, especially in partition output and the exchange protocol and exchange operator and so on. So if we zoom into the driver part, the partition output is taking 42% of total CPU. And then the next one is exchange, 17%, and then hash join, also 17%. So within this partition output operator itself, so which is a small pie chart to the left, so you can see most of these were spent in serializer, like serializer appending, and also estimate serialize the row size also is the green part. It's like nearly 10%. And the CRC flush takes 31%, which mostly it's in CRC 32. All right. So we did some internal experiments by introducing a new optimized partition output operator and a new partitioning, iterative partitioning serializer. So I have implemented for flat vectors and array vectors and dictionary vectors, and I'm still working on those, but got some pretty good numbers so far. So for flat vectors, we can see there are over 15 times to over 20 times improvement. So this is done using exchange benchmark. All right, and array, so I did some simple tests as well, shows about 4 to 5, 6 times of improvements. And dictionaries shows improvements as well, like at least dozens times, but unfortunately I lost the data yesterday. It shows that it works. Other exciting ideas is that, so this partitioned vectors, in place partitioning. So it doesn't only work for partition output, but we can also use it for streaming aggregate or sorting. So I believe this will help streaming aggregate at least. So yeah, but this is something I'll do next. So other improvements including like improved CRC32 computation, which is not included in my numbers, in my tests, but thanks to Bingwei, so we are able to see that we can do 4 times faster than the current Folly CRC32 hardware function implementation. And hash partition function improvements. So we have 4 times improvements with streamlined loop and AVX2. And also range reduction improvement. Yeah, it's improved at least over 1 magnitude times. All right. So that's the efforts to reduce the CPU times. And we also see some pretty big contentions in output buffer implementation and the exchange queue. So for output buffer, so the basic operations like acknowledge, enqueue, get data, delete results. So they currently all require a global exclusive lock. So with a new prototype, so we can move all these to their single destination buffers instead of the whole output buffer. So meaning that when you're inserting into one destination, you don't have to lock the whole output buffer for all destinations. Yeah, and also, I also noticed that the exchange queue contention was pretty big. So inside of the exchange client request function, so substantial CPU, it's used in the mutex acquire and so lock and unlock. So the idea is that we want to replace this queue to a lock-free queue, so we can potentially use Follies, so it has several implementations there. Yeah. So the next steps includes like covering all data types, all types of vectors. Like, so we currently have, so we don't have map yet, and also that delta, or I forgot the name. So constant, and also nulls. I'm also working on this, the exchange side, the receiving side. So when I was looking at the profiles, I actually found a large portion of the CPU was spent in the memory deallocation of the serialized pages in the receiving side. So thinking maybe we can reuse this part of, so especially for local exchange, that we can reuse these memories. Yeah, and also, like I said, this output buffer and exchange queue contention. I'm still working on it. So, yeah, I still have some bugs to fix. Okay. Yeah, so that's the end of my presentation. Thank you.
Also, quick shout out to PrestoCon days happening soon. And any questions from anyone?
So in the production, when we put the UDFs and you put a library in there, at some point we have to upgrade the library. So how can I do it in a live system?
So I'm so sorry, could you repeat the question
Okay,
really quick?
so you registered library, okay, it is running. At some point, I want to upgrade that library to go to the next level. I'm not changing the name of function or anything. How can I do that while the system is running? I have existing queries that they're running, that they're using the current version, and then new ones hopefully will use the new one. Can you handle two libraries at the same time? And understanding while not affecting the existing queries running.
Oh, no, we don't do that.
Hmm?
We don't do that.
Yeah, I know. So that's a problem, right?
Yeah.
Because then you have to shut down, you have to quiesce the system. That's not an option.
Yeah, it's going to be multiple steps to make that happen. Yeah.
Yeah. So you have to have versioning over there.
Yeah, we have to.
And the runtime.
Yeah.
Lock the version for the existing query, and then new queries take a new version. So you have to put the token over there to handle this. Otherwise, it's a big problem.
All right. Thank you. Oh. Sorry. You have a question? Yeah. You just talk loud.
Thank you.
Yeah.
Just a question about the CT bit. For the inlining, does that only occur when like the CT is being used once, or does it occur if the CT is being used multiple times? Like in Postgres, there's like a not materialized keyword that can control whether you can push down the filter even if the CT is only being used the one time.
I believe we have a configuration to say like what is the threshold. So you can say that only like use CTE, I mean with the materialization when there's more than so many occurrences in the query. So we have a config for it, yeah.
Thank you.